Okay, hi, it's great to be here. I will present a new code injection technique by abusing binary translation cache files. Before we get started, let me introduce myself a little bit. My name is Koh Nakagawa. I am a security researcher at FFR Security. My main research interests vulnerability research and exploitation technique, especially for ARM-based Windows. Recently, I started macOS security and found multiple vulnerabilities on macOS, such as TCC, SLP, or gatekeeper bypass. I gave talks at Black Hat EU 2020 and Codeblue 2021. This is the agenda. First, I introduce ARM-based OS's emulation technologies and fundamental concept of macOS security. Then I talk about the Rosetta 2 internals very briefly. Then I show a new code injection technique named AOT poisoning and how to exploit it on macOS. Then I show a similar new code injection technique on ARM-based Windows and how to exploit it. And then summarize this talk and show key takeaways. So let's kick off. ARM-based laptops have been becoming very popular recently, such as ARM-based Windows and Apple Silicon Mac. This is because I think ARM-based laptops offer long battery life. According to the data from the research firm, ARM CPUs are expected to reach 25% of the laptop market share by 2027. That's great. But however, there are some difficulties for many users to switch from Intel to ARM because we still have many Intel-based applications. To overcome this difficulty, Microsoft and Apple provide compatibility layers such as x86 emulation technology and Rosetta 2. These technologies are transparent to users, so when you run Intel-based applications, these two technologies automatically translate or emulate these Intel-based applications. But translating and emulating are time-consuming, so reducing this is very important. So to reduce the amount of binary translation, these two technologies cache the binary translation result as files. According to the MSDN or Apple Platform Security, if you can run the same application twice, the previous translation result is reused and the binary translation is not performed twice. This caching mechanism and binary translation cache files can be abused. Previously, I have been researching how an attacker can abuse these layers. So let's quickly recap my previous research at Black Hat EU. In this research, I analyzed the binary translation cache files on ARM-based Windows named XTA cache file. Then I proposed a new code injection technique, XTA cache hijacking. This code injection is performed by directly modifying the binary translation cache files. This technique requires admin privileges for modifying binary translation cache files, but it has unique side effects that benefit the attacker. For more details, see my Black Hat EU slides and talk video. After this research, I wondered if there is a similar code injection technique on macOS Rosetta 2 because it has similar caching mechanism and binary translation cache files. Then I started to study macOS security and analyze Rosetta 2 internals. While studying macOS security, I quickly noticed that the macOS security model is no longer a traditional Unix security model. Starting from LCAP10, System Integrity Protection, or SIP, is introduced. SIP is a security mechanism that restricts some dangerous operations, such as modifying system files, loading kernel extensions, and debugging system processes. Due to this security mechanism, even root user cannot perform these dangerous operations. So SIP is also known as rootless, so even root user does not have full access to the system. For example, even root user cannot modify system files, so if we try to delete the ls binary, this operation is denied. Moreover, even root user cannot access some files due to the data vault. So root user is not got on macOS. Next, I also noticed that the crux of macOS exploits is code injection. The macOS security researcher, Ze Ebelbet, said the alpha and omega of macOS exploits is to run code in the context of other applications. But why code injection? This is because a macOS security mechanism heavily relies on the code signatures and its entitlement. On macOS, entitlements grant various rights to the applications. For example, applications needing to access some sensitive resources, such as camera and microphone, messages, should have proper entitlements. Without specific entitlements, applications cannot use these sensitive resources. But if we can execute code in the context of other applications that are allowed to access some sensitive resources, we can hijack trust of them and gain rights of these applications. So code injection is dangerous and strictly prohibited on macOS. So hard at runtime is enabled for almost all applications, and this restricts code injection by direct hijacking. But if we can find a new way to inject code on macOS, we can exploit it to access some sensitive resources, to bypass privacy mechanism on macOS. So I started to explore a code injection technique using Rosetta 2. Okay, next let's move on to Rosetta 2 internals and how to achieve code injection using this. Rosetta 2 is not installed by default. So when you run an application that needs Rosetta 2 for the first time, pop-up is raised like this. And if you click install, Rosetta 2 will be installed. This installation can also be performed by running the software update command like this. This does not require any user interactions. Please note that installing Rosetta 2 doesn't require root privileges. So if the system does not have Rosetta 2, an attacker can install it manually running this software update command. Rosetta 2 offers two types of binary translation: just-in-time or JIT, ahead of time or AOT. Typically, AOT translation is employed, but JIT translation is also used for running applications that generate dynamic code such as web browser. For AOT translation, translated artifacts are written to storage as a special type of Mark object file. This is called AOT file. It contains translated ARM64 code, and these files are located at VirDB OAH directory, which is protected by zip. So even root user cannot modify these AOT files. So unlike Windows, root privileges are not enough for modifying these binary translation cache files on macOS. Are there any ways to control contents of these files? So to explore this, let's move on to how Rosetta 2 works. First, I explain some components of Rosetta 2. Some binaries related to Rosetta 2 are placed under the library Apple USR libexec OAH and USR libexec Rosetta directories. Translate2 is a CLI tool for translating an x64 executable without running it. Translate2 is a vital in this talk and will be described in later. Runtime is a runtime library that is injected into a translated process. OAHD is a management demo of AOT files. It receives a file descriptor of x64 executable, then runs OAHD helper. OAHD helper is a translator of an x64 executable. Next, I show a very simplified execution flow to explain how these components interact. When you run an interface application that needs Rosetta 2, Rosetta 2 runtime is injected into this process. Then Rosetta 2 runtime sends a file descriptor of an x64 executable via Mark IPC mechanism. After receiving the file descriptor, OAHD runs OAHD helper by passing a file descriptor as a command line argument. After that, OAHD translates it into an AOT file. And the translated AOT file is created at VirDB OAH directory. And this created AOT file is mapped onto the translated process. This translation is performed for every x64 module if there are no previous translation results. After this translation finishes, Rosetta 2 runtime transfers its control to these AOT files if needed. Typically, AOT translation is performed automatically like this, but AOT translation can also be performed manually by using Translate2. By using this tool, we can create an AOT file of the specified x64 executable without running it. Its inner workings are to send a file descriptor of an x64 executable to OAHD daemon via MacIPC mechanism. As I said in the introduction, these created AOT files are cached and reused. This is reasonable because binary translation is time-consuming, so should not be performed multiple times. But how does Rosetta 2 determine whether the specified x64 executable was previously translated or not? So to do this, OAHD calculates a dedicated hash and uses it for checking. I don't know what Apple called this hash, but I call this AOT lookup hash in this talk. You can find this hash value by digging the VarDB OAHD directory, and if there is a directory corresponding to the AOT lookup hash, OAHD reuses the AOT file in this directory. It looks good, but how OAHD calculates the AOT lookup hash from a specified x64 executable? A possible candidate is calculating the cryptographic hash from an entire binary contents and file path, but it should be avoided from a performance perspective. So OAHD does not hash whole binary contents. Instead, it hashes a file header and file metadata and file path. The way to calculate the AOT lookup hash is as follows. OAHD calculates the SHA-256 hash from the full path, macro header, user ID and group ID, 3 timestamps, and file size. 3 timestamps consist of M time, C time, and CR time. M time is the time when the file data was last modified, and C time is the time when the file status was last changed, and CR time is time of file creation. Particularly important here is that code section of the target binary is not used for calculating the AOT lookup hash. So if we can modify the code section while keeping the AOT lookup hash unchanged, we can cause a hash collision of the AOT lookup hash. So by abusing this, we can force a target executable to use a different AOT file upon execution. So based on this finding, a plan to achieve code injection is as follows. First, modify the target executable and inject shellcode into it. Then, create an AOT file of it using translate tool. After that, restore the modified executable to the original one, but keep the AOT lookup hash unchanged. And run this executable. Since the AOT lookup hash remains the same, Rosetta 2 uses the previous AOT file for the execution. Then poisoned AOT file is used for the execution. So if we can modify the file contents without changing the AOT lookup hash, we can poison the AOT file and inject code through this. But modifying the file always updates timestamps. As I said, timestamps are used for hashing, so the AOT lookup hash changes. So how do we file contents without updating timestamps? A possible way to do this is to restore timestamps after modifying the file. This is a well-known time-stomping technique, but unfortunately, this does not work because C time is used for hashing. Of course, time-stomping always updates C time. So we cannot restore C time after modifying the file. So we cannot use time-stomping technique here. But I found interesting description of updates of timestamps while reading the older Unix specification of mmap. It says the C time and M time fields of a file that is mapped with map shared and plot write will be marked for update at some point in the interval between write reference to the mapped region and the next call to msync. If there is no such call, these fields may be marked for update at any time after a write reference if the underlying file is modified as a result. May be marked for update drew my attention because this phrase has been changed to shall be marked in the latest version. So that in the latest version, updates of timestamps becomes mandatory. But if macOS follows a little old Unix specification, writing to a file via mmap without calling msync might not update C time and M time. So to check this, I wrote a test program. This program opens a file and maps it onto the memory. Then it modifies the file contents in two ways and show timestamps. One way is that it modifies the file contents via mmap and calls munmap. The second way is that it modifies the file contents via mmap and calls msync and mmap. The only difference is the call to msync. This is the result of this experiment. If msync is not called, mtime and ctime are not updated, although file contents are changed. However, if msync is called, these two timestamps are correctly updated. So we can change file contents without updating timestamps via mmap if we don't call msync. So based on this, our plan to achieve inject code is as follows. First, modify the target executable and inject shellcode into it. Then create an AOT file of it using translate2. After that, restore the modified executable to the original one. But when restoring, we modify the file content via mmap without calling msync. Since this does not update ctime and mtime, so the AOT lookup hash remains the same. So when running the target executable, previous AOT file is used and the poisoned AOT file is used for the execution, and injected code is executed. So I will show some quick demo. First, I build a test application that displays hello world string twice. And run this application. And this application shows the hello world string twice as expected, and calculates the hash value of this executable, then update timestamps, and poison AOT file of it, and inject shellcode through this. Before running, calculates the cryptographic hash value again. These two hash values are the same, so that this executable is not tampered with after AOT poisoning. And run this executable. But surprisingly, this program doesn't show the hello world string. Instead, it launches a bin shell. This is because the poisoned AOT file is used for the execution. But after updating the timestamp of this executable and run it again, this program shows the hello world string. This is because the timestamp is updated and the AOT lookup hash changes. So the poisoned AOT file is not used for the execution this time. Okay, so this technique looks good, but there's a limitation. This technique cannot be applied to a signed executable. There are two reasons why this technique cannot be applied to a signed executable. The first is that this is due to the new security mitigation introduced in Apple Silicon Mac. In Apple Silicon Mac, in-place modification of a signed executable causes a program to crash when running. This issue was reported by applications developer, and Apple has made a guideline to avoid this crash. They said code signing information is hung off the V node within the kernel, and modifying the file behind that cache will cause problems. So you need a new V node, which means a new file that is a new inode. So note that this crash occurs even if you restore the executable to a valid signed one on disk. So to avoid this crash in AOT poisoning, we cannot perform in-place modification via mmap. So we need to create a copy of the target executable, but this always updates the timestamps, so which means a change of AOT lookup hash. The second reason is that OAHD does not accept an executable with an invalid code signature. So when we try to translate an executable with invalid code signature, translate2 exits abnormally. So we need to create an executable with valid code signature containing our payload. As I said in the introduction, MacOS security mechanism heavily relies on the code signature. So we want to improve this technique to be applicable also to signed executable. So how Apple fix this issue? Apple fixed this issue by updating the APFS file system at Bixel 11.6 and Monterey 12.01. After this update, write into a file via mmap without msync updates C time correctly. So we no longer modify the file contents without updating timestamps. Unfortunately, Apple did not assign CV to this issue, but acknowledged it to me like this. Okay, so this update of APFS prevents us from exploiting AOT poisoning, but is Apple's fix enough? After updating my macOS, I noticed that the way to calculate the AOT lookup hash stays the same. So the Apple's fix relies on the APFS fix. But macOS supports various file systems other than APFS, such as HS Plus or AXFAT and FAT32. So the APFS is not the only file system available on macOS. Fortunately, macOS has built-in HDI util command, and by using this command, we can create and mount various file systems locally. Since Apple's fix relies on the APFS fix, we can bypass it using other file systems. Next, I examined the timestamps of other file systems. While reviewing, I found an interesting feature of FAT32. FAT32 does not have C time. So restoring timestamps after modifying the code section does not affect the AOT lookup hash. So we can easily cause a hash collision of AOT lookup hash by time stomping technique on FAT32 file system. Okay, so we bypass Apple's APFS fix. Next, we must overcome the limitation of the previous AOT poisoning. It cannot be applied to a signed executable. There were two reasons. So we need to bypass these two restrictions. First restriction has already been bypassed because we no longer need in-place modification. So even if we create a new file, we can restore its timestamps on FAT32 file system. The second restriction can be bypassed by resigning with an ad hoc signature. I found that OAHD accepts an executable with an ad hoc signature. So after injecting our payload, we can resign it with an ad hoc signature, then translate it. It looks good, but we need one more step. Replacing the existing signature sometimes changes the macro header. This change affects the AOT lookup hash. Because the AOT lookup hash is calculated from the macro header, file path, and other file metadata. So we need to perform ad hoc signing while keeping the macro header unchanged. So to address this issue, I developed a new tool to perform ad hoc signing while keeping the macro header unchanged. Okay, so the steps to inject code are as follows. This is called AOT poisoning. First, create a FAT32 image and mount it with using HDI util command. Then copy a target executable to the mounted point. And modify the target executable and inject shellcode into it and resign it with an ad hoc signature. Then create an AOT file of it using translate tool. After that, restore the modified target executable to the original one, having the valid code signature, and restore also timestamps. Then run the target executable normally. So the poisoned AOT file is used for the execution, and injected code is executed. Okay, so we can inject shellcode into an x64 executable with AOT poisoning, even if it is code signed. Okay, so let's move on to how to exploit this technique. First, I show a TCC bypass. TCC stands for Transparency, Consent, and Control, which protects user sensitive data. If an attacker tries to access some sensitive data, a pop-up is raised like this, and without this user's consent, an attacker cannot access sensitive resources. For more details, there's a great research on TCC internals and its bypass technique, which is presented by Chubb and Boyce at Bracket USA and EU. So please check out their research. TCC bypass can be achieved by injecting code in the application that are allowed to access some sensitive resources. For example, CVE 2020-24259 is a vulnerability of signal that enable an attacker to access the microphone without a TCC pop-up. The root cause of this vulnerability is that all the signal had vulnerable to entitlements, allow DYLD environment variable, and disable library validation. So we can easily inject unsigned dirib into signal to access microphone. Similar issues were present on other applications such as Zoom. Of course, these issues have already been fixed by enabling this library validation, so we cannot exploit this anymore. But with AOT poisoning, we can inject code into applications even if it is code signed. Okay, I will show a quick demo of TCC bypass. Only Zoom is allowed to access the screen and record its contents. So applications other than Zoom cannot grab the screenshot without a TCC pop-up like this. Like this. But when we execute code in the context of Zoom, we can grab the screenshot without a TCC pop-up. Now injecting shellcode into Zoom and run Zoom to execute our code. Then show the captured screenshot. Okay, so we have obtained the screenshot. Without a TCC pop-up like this. Of course, library validation is enabled in this version of Zoom. Next, I show other exploitations. AOT poisoning has several benefits for an attacker to execute malware. First, an attacker can hide malicious payload in SIP-protected location. So it is hard to investigate the attack in the incident response phase because there is no clear indicator in the target executable. The actual payload is hidden in the SIP-protected location, so no AV software scan this file, even for macOS built-in Xprotect. Second, this method makes the detailed dynamic analysis difficult because it has anti-debugging functionality. When we try to debug the AOT poisoned executable with LLDB exits abnormally like this. So when an attacker executes malware with this technique, detailed dynamic analysis becomes harder. Next, move on to how Apple fixed this vulnerability. Apple fixed this at Venture 13, Monterey 12.6, and Big Sur 11.7. Apple assigned CVE to this issue and gave me generous bounty. Next, let's analyze Apple's fix. After this security update, we cannot execute an AOT poisoned executable. The OAHD checks the dynamic code signing status by calling the fan control with fout file supplemental command, so the code signing validation prevents this attack. Okay, the dispatch looks nice, but this Apple's fix relies on checking the dynamic code signing status. So this means that we can still inject code into unsigned x64 executable. So TCC bypass is fixed and we cannot exploit it anymore, but local attacker can still perform other exploitations, such as hiding malicious payload in an SIP protected location and making detailed dynamic analysis difficult by anti-debugging functionality, even for the latest version of macOS. Okay, so next, let's move on to a similar new code injection technique on ARM-based Windows. As I said in the intro, ARM-based Windows has caching mechanism and must check whether the specified binary was previously translated or not. So it must have hashes corresponding to the AOT lookup hash. According to the Windows internals, 2 hashes are generated based on the executable image path and its internal binary data. You can find these 2 hash values in the name of the XC cache file. The file name, these 2 hashes are called module header hash and module path hash. But how are these hashes calculated? Windows internals doesn't answer me. So let's analyze it. Module path hash is calculated from the NT device path name of the target executable. It looks good. Module header hash is calculated from the DOS header, NT headers, not including image base, and last write time. Last write time is the M time in Unix. As you can see, only M time is used for hashing. So unlike macOS, C time and CR time are not used for hashing. So we can easily cause a hash collision for the module header hash by time stomping the M time. So poisoning binary translation cache files on ARM-based Windows seems very simple, but the situation is a bit different. There is no translate tool for ARM-based Windows. So we need to run the target executable to create an XT cache file. So to address this issue, I created XTSC translate tool, which enables us to create an XT cache file without running the target executable. Of course, it does not require admin privileges. Its inner workings, I don't have enough time to explain how this tool works. So for more details, see the appendix of this material. Now we can poison the XC cache file like AOT poisoning. So the steps to inject code is as follows. First, inject shellcode into modify the target executable and inject shellcode into it. Then create an XC cache file of it using the XTSC translate tool. After that, restore the modified executable to the original one, and restore also the last write time. Then run the target executable normally. Then poison the XT cache file is used for the execution. This is XT cache poisoning. Fortunately, XT cache service happily accepts an executable with an invalid code signature. So we can easily apply this technique to a signed executable, unlike macOS. So next, how do we exploit this code injection? First, this technique can be used for backdoor PE file. Backdoor PE is typically used for achieving persistence, but this technique can be easily detected by inspecting the modified executable, because this technique typically adds new section and modifies the entry point of the target executable. But with XTA cache poisoning, we can backdoor PE more stealthy because the target executable does not change. Second, XTA cache poisoning can be abused for the user-assisted elevation of privileges. The UAC elevation prompt shows the origin of the target executable. If it has a valid code signature, the prompt shows the verified publisher, but if not, it shows a publisher unknown with yellow stripe. But if an attacker performs code injection with XC cache poisoning against the target, against the executable with valid code signature and runs it, the code signature remains valid, so the UAC elevation prompt shows the verified publisher. So chances are good that user unintentionally execute it with admin privileges. To exploit this, installer is a good target because it is typically executed with admin privileges and has a valid code signature. Okay, I will show some quick demo. Netcat listener is running on the left side, and on the victim side, we have obtained the shell with medium integrity. Now inject shellcode into the Adobe installer. This shellcode contains reverse shell payload. And run the Adobe installer. It takes some time. Yeah. This Adobe installer has valid code signature. So the UH elevation prompt shows a verified publisher. And the certificate chain is also valid like this. And after clicking yes, installation process proceeds. But on the attacker side, we have obtained the shell with high integrity. Like this. So we can create a file under the C drive like this. Okay, Microsoft says that this issue doesn't meet the MSRC bar for an immediate security update. So this issue is not currently being fixed. So you might think that fixing this issue seems simple because hashing the C time, so hashing C time along with M time solves this problem. But this is not enough because we can use the same file system downgrade trick on Windows. So we can create a FAT30 image locally, then copy the target executable to it, and then we can change timestamps freely. But the file system downgrade trick is not required on Windows, even if C time is hashed. This is because we can change C time. This is because we can easily change C time on Windows using NT set information file API. NT set information file can change C time and M time simultaneously. So we can restore C time after modifying the file, unlike macOS. So even if C time is hashed, we can still cause a hash collision for module header hash. Therefore, hashing C time is not the ultimate fix to prevent XC cache poisoning. Okay, let's summarize this talk. Rosetta 2 and Windows emulation reuses the binary translation cache files to reduce the amount of binary translation. So to check whether the specified binary was previously translated or not, these two technologies uses the dedicated hashes. And these dedicated hashes are called LT lookup hash and module header hash and module path hash. And these hashes are calculated from the timestamps and the header of the target file and the file path and other file metadata. And I propose two new code injection techniques named AOT poisoning and XC cache poisoning, and which are achieved by causing the hash collision of the dedicated hash. And I also cover the details of these techniques and how to exploit them. And key takeaways from this talk. For Red Teamer, I published POC code on GitHub. Please check these repositories and please test your own environment. For security researchers, to our best of knowledge, there are few studies on this topic, but as an ARM-based OS becomes popular, attacker likely targets these. So I hope to see more vulnerability research on this topic, and I hope this talk will be the starting point of your research. For OS developers, as I show in this talk, failure to check the file identity correctly causes a security vulnerability to enable code injection. So determining the file identity is difficult. So implementing this correctly needs more consideration. So for everyone, be careful of this threat. Since ARM-based laptops are becoming more popular, An attacker will likely exploit this. And that's all. Thank you for your kind attention. Sorry, I don't have enough time for Q&A. So if you have any questions, please ask me later. Thank you.